Okay, so one thing I hadn't covered but is very synonymous is control volume analysis that occurs for all this differential fluid stuff. And it's just taking an integral approach as to a differential approach with that material derivative type thing we developed. So just as an example, right, control volume analysis is, say you have some sort of thing like a box, a black box, whatever it could be. It could be like even like a little vent. So let's even say this thing goes down right here. And there could be fluid going in here and then leaving here. A control volume analysis, what it does is you just draw some arbitrary box around your system, and then you pose all the exact same laws. You just need to always know to add this flux term is what it's called. So real quick for conservation of mass, what you say, right, 0 needs to be a time rate of change. So density in here, right? So this is the change of the mass inside of this control volume. And then on top of that, you have this additional term. This bigger. And then there's also the incoming and outcoming, which is a flux term. So that would be a rho of V dA, where that's your little normal vector outside of your thing. So what this represents is the time rate of change of mass inside of the control volume, and then this part is a flux term. So what rate, the difference of whatever came out minus whatever came in. Okay, so then you push this inside the integral because it's continuous, blah, 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 becomes a partial derivative. Then with this, you apply something called the divergence theorem or Gauss's theorem. It had many different names, and all it does is it lets you not integrate area or integrate around this surface, but convert it to a volume integral, and that changes to this. All right. So this is something that came from math analysis and came from Calc 4 and vector calc, where you then convert surface integrals to volume integrals. So the divergence theorem is a tool that we can use for control volume analysis to convert any sort of surface flux term into a volume integral. Now for conservation of mass, the time rate of change of the internal mass plus the flux of the mass needs to equal 0. And I can't generate mass inside the control volume. Okay? Now what you do is you now connect these two integrals, and you'll get that familiar expression that we already had before. Okay? So then you have this expression. Notice this is the exact same thing that we had when we did the material derivative thing. You just then say, well, this dV is a non-zero quantity. It's always some little tiny amount of volume. So that means if this is going to be 0, this term right here has to be 0 throughout the entire body. So then you can just take this part off and then take that part off, and you get the exact same relationship. So control volume analysis is always going to take some internal change based on it. So you have to think about it in integrating little bits of volume, and then a flux term where you look at the in minus the out. And then you connect them with the divergence theorem, and then you get a relationship. So that is a classic control volume application where we derive the exact same continuity equation we had before. This is even before we had incompressible fluid, when this term right here was a constant. And I'll do the same for another one in the next video.